In this lecture, we will talk about the numericals based on vertical circular motion. So let's start with numerical number first. It says that a particle is suspended from a fixed point by a string of length 5 meter. So this is our diagram relevant to that. This is a string and a particle is suspended having 5 meter length. It is projected from the equilibrium position with such a velocity that the string slackens after the particle has reached a height of 8 meter above the lowest point. So let's take that we are considering a vertical circular motion. So this is our vertical circular motion, okay, and this is the particle. Initially it is in the equilibrium position and having length 5 meter. So it's saying that it reached a height of 8 meter above the lowest point. So obviously the 8 meter height somewhere here, okay, this is the center. So this is the radius and the corresponding height is from the center is 3 meter. This is 3 meter. Then 5 meter plus 3 meter is equal to 8 meter and this is 5 meter. So by little mathematics, this is, we see that this is 5 meter, this is 3 meter, so this length will be 4 meter, okay. So this is comes out to be 4 meter and this angle comes out to be 53 degree. So now what it says, find the velocity of the particle just before the string slacken. So at this point position, let's say at this point P, the string slacken, it means that the tension becomes 0 but the speed is non-zero. Velocities or speed is non-zero at point P. Find also to what height the particle can raise further. Okay, so firstly we will calculate the velocity at point P. Okay, all right. So let's consider that we supply a speed of u at the lowest most point. So from the conservation of energy between the point A and P, we can write equation. Solution: conservation of energy between point A and P. So at point A, the kinetic energy is 1 by 2 m u square and the potential energy is 0 because I am considering this as the reference level. So at the reference level, I am considering the potential energy is 0, equals to, at point P, the kinetic energy becomes 1 by 2 m v square plus the potential energy mgh. What's the value of h? It becomes 8 meter. Okay, this is a very simple equation. Okay, this is one of the equation, and the second equation at point P is based on Newton's second law, that's the net force toward the center is equal to centripetal force. So we can see here also that in this direction the force is acting mg cos of theta. Okay, so I can write at point P, I can write mg cos of theta. Theta is what? Theta is 53 degree plus tension equals to mv square upon r. We can write this, but at point B tension becomes 0, but at P tension T becomes 0. So we will substitute T is equal to 0. We will get mg cos of 53 degree equals to mv square upon r. This m terms cancel each other. So you will get, let's put the value of g is equal to 10 and r is equal to 5. So this is 10 multiply 5 and cos of 53 is 3 by 5 and it's root. So this is the speed. When you calculate it, it comes out to be, this 5 term cancels, this 30 meter divide second. Alright, so this is our velocity which is asked in the part A. find the velocity. So we calculated the velocity at point P. Now at what further height? So the situation is something like this. This is our point P. Now the particle has some velocity v. Okay. So you see here that this angle is 53 degree. So this angle comes out to be 37 degree. 37 degree. So obviously this angle again become 53 degree. So the particle at point P is projected with a speed of 53 degree. So it will follow a projectile motion, something like this. So we need to calculate the height achieved. This height achieved, the maximum height achieved by the particle. So we will use the formula of projectile motion. What it says, u square sine square theta upon 2g. This is the formula we will use. So it comes out to be u square, it means root 30 square, 2g equals to 10, sine square theta, value of sine of 53 degree square. When you put the value, you will get 6 by 5 meter. So this is the height achieved further by the particle from point P. So in this way we calculated the velocity as well as the further height achieved. Okay. Let's move to numerical number second. Numerical number second says a small box of mass m is kept on the fixed smooth sphere of radius r at a position where the radius through the box make an angle of 30 degree. So already it is making an angle of 30 degree. So let's try to draw the sphere. This is our sphere and this is the center of the sphere. Let's say this is the vertical line and the sphere is making an angle of already 30 degree. So sphere is somewhere here, the box is somewhere here. Okay. At a position where the radius through the box make an angle of 30 degree with the vertical, the box is released from the position. It means that the speed here is 0 because the box is released. What is the force exerted by the sphere on the box just after the release? So just after the release, still we are considering the block is at rest. So it is not under the centripetal force, we can say, because just after the release is a situation when still the box has a velocity 0. So what we can write here then for part A, we can simply say that as the gravitational force is acting downward, which is mg, this angle is 30 degree. So the force acting, the component of mg in this direction is equal to mg cos of 30 degree. So this is mg cos of 30 degree in this direction and the normal is acting opposite to mg cos of 30 degree. So n normal, n is the force exerted by the sphere on the box, which we need to calculate, right, by the sphere on the box. So n is the force, we need to calculate n. How we can calculate n? We can write mg cos of 30 degree equals to n. This is very simple. So n equals to mg cos of 30 degree. Cos 30 degree comes out to be root 3 by 2. So this is our answer of this part. Let's move to part second. But find the distance traveled by the box before it leaves the contact with the sphere. Let's consider that the box came somewhere here before it leave the contact, somewhere here. So it is making an angle of theta now. Okay. So the component again, now mg is acting this way and the component of mg towards the center is mg cos of theta in this direction. This is quite fine. Normal will act in this direction and it's moving with some velocity v. This is the situation. But at point P, the box leave contact with the sphere. It means that the normal reaction at point P will becomes 0. Okay, so let's solve this. We will write the equation at point P. So for point P, we can write mg cos of theta negative n equals to mv square upon r. This is our very fundamental equation from the Newton's second law corresponding to centripetal force. Now put n equals to 0 here. Put n equals to 0 because the box leave the contact from the sphere. So we get mg cos of theta is equal to mv square upon r. Okay. So m terms cancel each other. This is gr cos theta is equal to v square. Let's say this is one of the equation. We will use it further. Okay. Let's say this is equation number 1. Now we will apply the equation for conservation of energy between the points A and P. Let's say this is point A and P. So apply conservation of energy between points A and P. So the kinetic energy at A, as the block is released from rest, so the kinetic energy at A is 0. Potential energy at A equals to kinetic energy at P plus potential energy at P. Kinetic energy is 0, but the potential energy is equal to mg r. You can see here. This is r and the height from the reference level. Let's say this is our reference level. This is our reference level. This is our reference level. So this height, it becomes r cos 30 degree. R cos of 30 degree. This one. Okay. So we will put mgr cos of 30 degree equals to, at point P the kinetic energy is simply 1 by 2 mv square, where v is the variable, and the potential energy at point P is equal to mg r cos theta. So we will solve this equation. We can write it as, this is m terms cancel. So gr cos of 30 degree, cos 30 equals to root 3 by 2 equals to v square by 2 plus gr cos of theta. So we can see from the equation first, gr cos theta is equal to v square. So we will use the value of gr cos theta in this equation. So this is gr root 3 by 2 equals to v square by 2 plus v square. What we get? We get gr root 3 by 2 equals to 3 by 2 v square. This is what we get. Okay. So from this equation we can get the value. These two cancel each other. So we can have v square is equal to, or v square upon r is, we can write gr root 3 by 3 equals to v square. So we can use this according to our requirement. Okay. Because we need to calculate the length, find the further distance. How we calculate the distance? You know arc method. We will apply the arc method here. What's the arc method here? Something like this. This one. So the particle move from here to here. So let's say initially the particle, the distance was L1, which corresponds to angle theta 30 degree, and let's say finally it corresponds to this, which corresponds to angle theta, and corresponding to theta the distance covered is, let's say, L2. So what's the net distance covered? So net distance covered is equal to delta L, which comes out to be L2 minus L1. So this is the distance covered by the block on the sphere. Okay, so let's calculate that. Before that, we need to calculate the value of theta. What's the value of theta? So we have our equation number second, this one. So you can see in equation first we have v square here. In equation second we have v square here. We can equate v square from first and second equation to get the value of theta, because we have cos theta. So let's do that. From equation first and second we have gr cos of theta equals to gr upon root 3. Gr term cancel each other, something like this. So theta comes out to be cos inverse 1 by root 3. So this is our angle theta, which we will use. This is equation number third. Now the distance covered. So delta L equals to L2 minus L1. Delta L equals to L2. L2 comes out to be r theta minus and r 30 degree. In this way, we can write r theta negative 30 degree is equal to pi by 6 in terms of radian. So delta L equals to r is common. Theta is what? Cos inverse this one negative pi by 6. So this is our required answer of the problem. This one is the required answer of the problem. Okay, it's a very interesting problem, so you need to practice this problem multiple times to understand the concept behind it. All right, let's move to numerical number third. Numerical number third is again very interesting. What it says, have particle hanging from the fixed point by a light inextinguishable string of length L is projected horizontally with a speed this much, root of gl. Find the speed of the particle and the inclination of the string to the vertical. So we need to calculate, find the speed and the inclination of the string to the vertical at the instant when the tension of the string equals weight. At this condition, we need to calculate the speed and angle theta. Okay, no problem, we will calculate that. So what's the situation here? Situation says that we have a circle, vertical circular, and let's say this is the center, this is the particle, and at some instant the particle is somewhere here and it's making an angle theta. The initial speed supplied is equal to root gl in this direction, root gl. Okay, so here it gain a speed of v. You know, mg is acting downward, gravitational force is acting downward, so we have a component of mg in this direction as well as in this direction, and this component, this angle also becomes theta, so this becomes mg cos of theta, and the other one is mg sin of theta, and the tension is acting in the string towards the center of the circle. Okay, so this is the free body diagram here. Now we can write the two equations. First is the Newton's second law, which corresponds to centripetal force, and the other one is the conservation of energy. So from the Newton's second law, which corresponds to centripetal force, we can write T negative mg cos of theta, because the tension is acting towards the center, so tension must be greater than the mg cos theta, equals to mv square upon L. L is the length of the string. Okay, now according to the condition, what we have, tension must be equals to weight. Weight is equal to mg. So we will substitute this value in the above equation. What we get? We get mg negative mg cos of theta equals to mv square upon L. So mg becomes common. 1 minus cos of theta equals to mv square upon L. So something like this we will get. Okay, so let's say this is our equation number first. We will use it in further calculations. Now apply the equation based on conservation of energy. Now conservation of energy, apply conservation of energy equation. Let's say this is our point A, this is point B, between A and B, between A and B. Okay, so at point A, the kinetic energy and the potential energy equals to the kinetic energy at B and the potential energy at B in this way. Kinetic energy corresponds to U, so we can write 1 by 2 m u square means GL plus potential energy is 0 because we are considering the lowest as the reference level. This is our reference level, equals to kinetic energy at B is equal to 1 by 2 mv square plus mg. So this is the height gained, this is the height gained, and this height will be L, and this value is equal to L cos of theta. So L negative L cos theta, L negative L cos theta is equal to H. Okay, so let's solve it further. So it becomes mgl by 2 equals to 1 by 2 mv square plus mgl 1 minus cos of theta. Okay, now from first we can have mv square upon L, we have some values, so we can use the equation first and second. So we can use the value of mv square from equation first and substitute it in this equation. So we can write mg L, or we can solve this equation something like this: mgl by 2 plus 1 by 2, then mv square we can write mgl 1 minus cos of theta plus mgl 1 minus cos of theta. Okay, so let's solve this equation. So from this we can get the value of theta because v is nowhere here. Okay, let's solve this. mgl terms cancel each other. mgl, these terms cancel each other. So we are left with 1 by 2 plus 1 by 2 negative 1 by 2 cos of theta plus 1 negative cos of theta. Sorry, here equals to sign is equal to sign. Okay, so what we have now, these half terms cancel each other, so we are left with half cos of theta plus cos of theta equals to 1. So it's become 3 by 2 cos of theta equals to 1. So cos of theta is equal to 2 by 3, and theta comes out to be cos inverse 2 by 3. So this is the angle what we need to calculate, inclination. So this is the inclination made by the light string with the vertical. So this is the inclination which is the required according to the numerical. The second thing we need to calculate is the speed. Okay, and speed equation is from the first equation. We know the value of cos of theta. Yeah, So cos of theta is equal to 2 by 3. We will substitute the value of cos of theta in equation first. So let's say from equation first, we have mg 1 minus cos theta equals to mv square upon L. Let's put the value. So mg 1 minus cos of theta, here cos of theta is equal to 2 by 3 equals to mv square upon L. M term cancel each other, so it comes gl 3 minus 2 is equal to 1 by 3 equals to v square. So gl by 3. So this is the answer of this numerical. Velocity and the inclination made by the string with the vertical. Okay, again this is very important and numerical. Please try it, practice it. So let's move to numerical number 4. So numerical number 4, what it says a particle rests on the top of a smooth hemisphere. So in this situation we have a hemisphere. This is our hemisphere. Okay, and it is smooth. A particle rests on the top of the, so let's say this is the top here, and the radius is r. It is imparted a horizontal velocity. So this particle gains some horizontal velocity. Let's say u is equal to root of neta g L. Find the angle made by the radius vector joining the particle with the vertical at the instant the particle loses contact with the sphere. Let's say at somewhere here the particle loses contact with the sphere, somewhere here. So we need to calculate the angle theta, find the angle theta. Okay, let's solve this. Firstly we will draw the free body diagrams. You know that mg is acting downward, so the component of mg towards the center is equal to mg cos theta, mg cos of theta, and the normal is acting in this direction. So it has some velocity v at, let's say this is point B, this is point A. Okay, so from the Newton's second law equation, centripetal force can be written as, we can write the centripetal force something like this, mg cos of theta negative normal equals to mv square upon r. But here at point B the block lose contact, right? The particle lose contact. So when there is no contact between the particle and the block and the hemisphere, the normal will be 0. So I am substituting the value mg cos of theta equals to mv square upon r. M term cancel each other. So in this way we will get our v square upon r, or we can say v. So it is gl cos of theta root equals to v. Let's say this is our equation number first. We will use it in the further calculation. Now our second equation comes from the conservation of energy. Let's apply conservation of energy. Conservation of mechanical energy. So kinetic energy at A plus potential energy at A equals to kinetic energy at B plus potential energy at B. So here our reference level is this. This is our reference level. Where the potential energy is assumed to be 0. Okay. So kinetic energy at A is equal to 1 by 2 m u square, which comes out to be neta g L, and the potential energy is equal to mgr equals to kinetic energy is equal to at B is equal to mv square, and the potential energy equal to mg h. H is equal to what? This is h. This is the height of the block. This is h, which is equal to r cos theta. So it is r cos theta, r cos of theta. All right. So this is our let's solve this further. Mass term cancel each other, masses cancel each other, and then we can write neta gl by 2 plus gl and neta gl. L is what? I think there should not be neta L, there should be neta GR, because L corresponds to length of the string and R is the radius. So keep in mind L equals to R. Okay. So I am substituting L equals to R. So it will become neta G R. So this is R. This is R. Okay, this is R. So this is R, neta G R. So neta G R by 2 plus G R equals to V square by 2 plus G R cos of theta. Okay. What we have from our equation, first we can write it as something like this: if V square is equal to GR cos of theta, right? And we can substitute this here, GR cos of theta. What we get? Neta GR by 2 plus GR equals to V square by 2 plus what we get? GR V square, something like this, right? Now solve it. We get GR neta by 2 plus 1 equals to 3 by 2 V square. Okay. And what we need to calculate? We need to calculate, find the angle. We need to calculate angle. Okay, that's fine. Then further we can solve the situation here. So from this we get the value of V. You can write the value of V. R is not given, so V square upon R in terms of neta we get the value. Okay, we will use this result in the further calculations. Let's move to equation. So we can say, yeah, here we can use this equation and the equation first. Both have V squares, so let's calculate theta from that. This is GR neta by 2 plus 1 equals to 3 by 2 V square is equal to GR cos of theta. GR term cancel each other, GR cancel each other. Okay, and then we have 2 by 3 neta by 2 plus 1 equals to cos of theta. So this is what we get in terms of neta. Okay. So this is 2 by 3 neta plus 2 by 2 equals to cos of theta. This term cancel each other, so neta plus 2 by 3 equals to cos of theta. And finally theta comes out to be cos inverse neta plus 2 by 3. So this is our the final answer of this example. So I hope you understand this, how we calculate, how we use the values in different equations. So these are the four numericals based on vertical circular motion, and these are very important. So keep practicing these numericals so you understand the concept very well. See you in the next lecture. Till then, bye bye.